Okay, so 12.2, we're going to start actually talking about some calculus.
Finally.
Prior to now, we were just kind of learning some of the background needed to understand what this stuff does or what it means. I'll tell you though, as you guys finish the coursework for Calc 3, this is just a small snippet of what everyone usually remembers with Calc 3. Usually when people say, oh, what did you do in Calc 3? You'll say, oh, we did partial derivatives, we did multiple integrals, we did all this cool stuff, but that's later. This is not a multivariable calculus quite yet. Anyway, so we'll go through pretty much your sequence in Calc 1, which was first, before you learned calculus, you talked about limits, right? After you talked about limits, what came next? Derivatives. And after you talked about derivatives, then you did applications. We'll do one, very easy one. And then integrals. Okay, so that's what we're going to do with vector valued functions. So first we'll talk about limits and continuity. Okay, and when we're talking about a limit, remember that we have this happy parametric curve cruising along, and we have vectors that we have connected that generate that curve. Okay, now the definition looks something like this. Yes?
Why are you using R like the vector on T?
That's what the yellow curve is R of t.
Why is it
It's a vector valued function. It's not a vector.
why would you use like a vector valued function versus just a normal function?
Because it's just, there are different ways to interpret things. So, I mean, you could use the parametric equations or just a normal function. But when we start doing physical applications later on, we are interested usually in position vectors, velocity vectors, and acceleration vectors and stuff like that. So if we have a framework that works already with vectors in the system that we're in, then interpreting that is very easy. That's the short answer I can give you. Okay, so the definition looks something like this. The limit as t approaches a of the vector valued function r of t is equal to some limiting vector L if and only if the limit as t approaches a of the magnitude of r of t minus this limiting vector L is 0. In other words, all this means is that the limit, and I can kind of zoom in here. So as we get close to this a value, perhaps this is the limit that we're looking at. So as we get closer to a, these vectors' components start to be exactly the same as the L vector that we have here. So obviously if we subtract, if I were to plug in a, and we're saying that the components are becoming very close to the actual limit, those components will be the same so that when you find the magnitude of the difference, it's going to be 0. Okay?
So this means your limit is a vector.
Yes.
Like a value.
Yes. So when you take the limit of a vector valued function, you're going to get a vector, particularly the vector that connects from the origin to somewhere along that parametric curve, depending on what that value is. Jacob.
So, I'm looking at this. The limit of something is equal to this vector if that vector is itself.
Pretty much.
Okay.
Which is, if you put it that way, I mean, that's kind of what a limit was last year too,
Yeah.
right? Yes.
What's the A in this situation?
What is the A? So, yeah, it's a particular, so R of A, we're going to say is approaching L. So as we get closer to A for time, or whatever parameter we're using, it's going to produce this limiting vector, vector L. Okay, so it's a specific time value. Okay. Let's go back to black.
Can you draw on?
It's right here.
Oh, it is.
Yes. Mm-hmm. Okay. What's what? Theorem. Sorry. If R of t is equal to some vector x of t, y of t, then the limit as t approaches a of R of t would simply be the limit of the components. So the limit as t approaches a of x of t, and the limit as t approaches a of y of t. And again, provided the limit exists. Okay, so finding limits, really it's no different than what you've done before, at least right now, until we introduce multiple variables. It's just you have a few of them to do. So if you remember how to find limits, you're just going to do 2 of them in one problem, or 3 of them, depending on how many components there are. So for example, if we had R of t equals ti plus the square root of 1 minus t times j minus 4 times cosine t k, we wanted to find the limit as t approaches 0 of R of t. What do you suppose you would do?
Plug in 0 on Q.
First, you plug in 0 for t. If there are no issues, that's the limit, right? So if you plug in 0 for t, and again, I'm just showing the work. You take the limit as t approaches 0 of the x function. You take the limit as t approaches 0 of the y function. And you take the limit as t approaches 0 of negative 4 cosine t. Bless you. And we get a vector out of that. What is that vector? 0, 1, and negative 4. Very good. Questions?
That's it?
Yeah?
Wait, so what happens if it doesn't work out nicely?
If it doesn't work out nicely, then you have some tools that you probably learned along the way, like factoring, L'Hopital's rule. Okay?
We just use like calculators.
No. You must know in here what is going on. Okay. Continuity. We say a vector valued function is continuous at a point t equals a if the limit as t approaches a of r of t is exactly r of a, which is what we did in the previous example. So in the previous example, we know for sure that this vector-valued function is continuous at 0. Why? Because the limit exists and we get exactly the same value. Now, as far as an interval is concerned, so let's say we have r of t here, and maybe from this point to this point represents an interval I. We say that a vector-valued function is continuous on I if continuous at each point in the interval, with the exception of something. What do you think?
Endpoints.
Yes. Just like before, right? Any questions so far about some basic limits and continuity definitions? Okay, so after limits, we talk about derivatives. If r of t is a vector-valued function, the derivative of r with respect to t, which we'll just use a little prime notation, is the same thing as finding the limit as h approaches 0 of
R
There
of
you
t
go.
plus h
Minus
r of t plus h
minus r of t
minus r of t.
all over h.
Very good.
How would that
The definition of the derivative. Now some other notations. We sometimes go just r prime without the of t. You could also go dr dt or d dt of the function r of t. So all of these things mean the same thing. Okay, so now what is going on when we take the derivative of a vector-valued function? So, is everybody good with what I've done so far? No one needs this? Okay. Let's use all these new colors to choose from. I was at Target yesterday. I got like the multicolored pen pack. So exciting. Okay. None of you care. That's all right. So, let's say we have some parametric function or vector valued function, r of t, and the orientation looks like it's if we had a clock, counterclockwise-ish. Okay. Now, geometrically, so here's what's going on. R prime of t is a vector tangent to the curve at the tip of R of t. And it points in the direction of increasing parameter. So, hold on, direction of increasing parameter. So, if I drew R of t, or a particular value, so let's say that this is the specific R of t vector that connects to the curve represented by the whole R of t equation. When you calculate R prime of t, you're going to get a vector that's tangent to the curve but also pointing in the direction that it's increasing. So it's going to have to look something like that. Okay, so that's what the derivatives of vector-valued functions look like. They tell us tangent vectors at the endpoint of R of t. And it tells us the direction of motion, if we wanted to think of this as motion, which we will later. But as far as actually differentiating things, here's another theorem. One that I expect you to be able to prove. No hint implied. Given R of t, R of t is differentiable at t if and only if each of its components is differentiable at t. In which case, the component functions of R prime of t are simply the derivatives of the corresponding component functions or components of R of t. I wrote out a lot because it's important to know what we're about to do here. What this theorem is saying is essentially that R of t is differentiable as long as we can differentiate each of the components. And if we can do that, then that's the derivative of R of t. It would just be the derivatives of the components of R of t. Okay? So, to prove it, we start by what we're given. We're given a function R of t, right? So let's define it. Let's suppose R of t is f of ti plus g of tj. I'll just do 2 dimensions. You can argue that if we had a third, it'd be the same exact proof, just with an extra component. Now, if we want to go ahead and calculate R prime of t, how do we find the derivative right now? You take the limit as h approaches 0 of Good.
minus I of t over h.
Good. So we know that much, because that's what we've talked about, right? We know what vector valued functions look like. We know that to find the derivative of a vector valued function, you just have to use the definition. So now, this is true as long as, and now we've also talked about taking limits of vector valued functions, right? If we're taking the limit of a vector valued function, you take the limit of the components. So you can do the limit as h approaches 0 of, let's go, x component. So that would be f of th, or f of t plus h, sorry, minus f of t all over h. That's your I component. And we're also going to take the limit as h approaches 0 of your j component, so g of t plus h minus g of t all over h. Okay, so what symbol? If and only if.
Oh, that's what you're writing at?
Get the I double F and
Sorry, yeah.
Oh. What? I thought those were
So there's two things in mathematics that you kind of, and you know, those of you that will go on and take more math courses, there's this, which means implies. Like this step implies the following step, which implies the next step, right? And if we're using if and only ifs, that means that you can't have one without the other. Okay, so that not only can you go forwards, you could also go backwards. Does that make sense?
That meant like an arrow. Yeah, I thought they were arrows.
Well, the first time I did this in Calc 3 when I was teaching it, someone thought it was a sideways smiley face. They're like, why do you keep doing that? I'm like, what are you talking about? Drawing sideways smiley faces. I'm like, I don't see what you're talking about. Anyway,
Wait, so do we have to like write this in our proofs?
you should, yes, actually.
Oh, okay.
Yeah.
Okay.
If-
okay.
So look, here's the premise. Here's what you should know so far, because this is a proof that you should know how to do.
Oh, great.
We started with what we were given. We were given R of t. So what did we do? We actually wrote out what R of t looks like. You could have used x's and y's if you preferred. I used f's and g's. Same thing. Then we wanted to figure out what the derivatives look like. Well, we know that to take the derivative, we have to do the limit of the vector valued function. We talked about that. We've also talked about taking limits. To take limits, you take the limits of each component of the vector valued function, right? So we haven't done anything that we haven't talked about yet. But what's this represent? If you ignore everything else, the derivative of f, right? So that's exactly f prime of t times I plus g prime of t j. And we've pretty much proved what we needed to prove, that if we're going to take the derivatives of vector valued functions, all you really need to do is just take the derivatives of the components.
Is that a freeway? Or what is that?
This,
Yeah. Okay.
that means that this is the end of the proof.
Oh.
what is it?
I thought they wrote usually they write like those little triangles.
Sometimes you'll see this, which I think was Latin for I don't remember. Quo erratum demonstratum or something. That which was needed to be shown has been shown, is what that translates to.
Okay.
Yes.
So it would be the same thing if instead of you did like the I hat and J hat, you just kind of wrote it out in like vector format.
With component notation?
Yeah.
Absolutely.
Okay.
Absolutely the same thing. Mm-hmm.
Is this just saying if you take the derivative, you get the derivative?
No, this is saying that to take the derivative of a vector valued function, you take the derivative of the components. That's what it's saying.
Okay, what's the same thing?
Yeah. It's like, how is that saying anything different? Like, it's just.
Well, here's the thing, okay? Remember when you first learned how to take derivatives, you had to use the definition, right? And then eventually you came up with shortcuts and rules and like, oh, we just know that derivative of x squared is 2x or whatever. we haven't talked about how to take derivatives of vector valued functions yet. So this is basically laying down the framework that we don't have to use the definition of the derivative to find the derivatives of vector valued functions. We can just do the derivative of each component.
It's like if you take the limit, you can.
Yes. And now that we've proven it, we don't have to like do that anymore. Because you guys know how to find derivatives of just the components already. You would hope, yes. Let's try some, just to make sure.
Wait, aren't we like
forgotten a lot of
doing
trick
this kind of in physics right now?
I don't know. I don't know.
He's not your physics teacher.
Boom, boom.
But like we took derivatives of vectors, so it's basically.
So yeah, that's pretty much.
Yeah, but you guys just assumed that you could do that.
Yeah, physics assumes a lot of things. We like to prove why things work in math. Okay. So let's say we have r of t equals 1 over t natural log t
Oh.
and e to the 2t.
Wait, that first symbol, is that a T?
1 over
Is
2.
that-
1 over t.
1 over 2.
Wait, 1 over.
Looks like a
Oh! I thought
That's like
it
a
was like a T with like a little line through it.
No.
That's like an upside
1
down
over
That looks like a
T.
guy
But
with
they're
a-
connected.
That did not help it.
Sorry, YouTube followers, my class is a little picky.
Wait, you're recording?
Yep. Surprise, you're on video.
Still looks like it.
Is anyone not?
Yeah, once it's seen, it cannot be unseen.
Are you gonna be recording every day?
I'm recording today because we have someone that needs the lesson because they're not in class. I only record if I know, for instance, that someone's absent and if I don't have it already. Anyway, what's that? No, because no one knows who you are.
Andre Cristobal.
Okay.
Just go back and edit that. Okay. All right, miscellaneous student named Andre. What is the derivative of this vector valued function going to give us?
1 over t squared.
So close.
Negative 1 over t squared.
And what's the next component?
1 over t.
And
2
2e to the 2t. Do we need another derivative example? We're good?
And trig stuff is the same, right? Like.
Yeah, all the same rules. Trig, law, everything's the same. Let's finish with writing the derivative rules, and then we're done.
And trig rule is the same? Like review? Like old rule?
No, like with vector valued functions, like properties. Not like, here's how you differentiate sine. It's cosine. Or
So we have to.
you have to know that, yeah.
I'm sure.
R of t, R1 of t, and R2 of t are all vector valued functions. Okay, so that's obviously what we're working with here. F of t is a real valued function, just a normal function. That's what RVF means. K is a scalar, so I'm just defining all the notation you're going to see. And C, with the little vector, is a constant vector. Okay, here are the rules. If you take the derivative of a constant vector, what are you going to get? 0 vector. Good. If you take the derivative of a scalar times a vector valued function, this is the same as what?
Scalar times
Good. If you take the derivative of the sum of two vector valued functions. That one's easy. It's just the derivatives of each added up. And if you take the derivative of a product, say R1 times R2. Oh, you know what? Let's not, that's later. I'm thinking dot product. Scratch that. Sorry. Derivative of a real valued function times R of t. So if we have the product of a real valued function, not a scalar, and R of t, since they both have t's, when you take the derivative of a product, you have to use the product rule.
Prime of t
So f of t times
r prime of t
r prime of t.
Plus the
plus f prime of t
Yep,
times r.
it doesn't matter how. Some people write it the other way, f prime plus r, and then,
people write minus negative.
yeah, those crazy people.
So subtraction doesn't make sense.
All right, that's a good place to stop. Tomorrow we'll pick up with tangent lines and go on to some integrals. Quotient rule is the same as the product rule, really, if you think about it, right?